Thank you for that very kind introduction. It's such a pleasure to be here, and so exciting to see so many of you here, packed room. I love the energy. So I'm going to talk about what I see as the future of programming, which is both different from how we've been doing it, and I think much more exciting. We'll start with a quote here from my favorite American philosopher.
To alcohol, the cause of and solution to all of life's problems.
To alcohol, the cause of and solution to all of life's problems. What I really like about this joke is that if you replace alcohol by AI, it's still funny. And that's very much the theme of this talk. Bugs. Can't look at any newspaper or website these days without people freaking out about Mythos or some other powerful tool, AI tool that can be used for cyber attacks, finding vulnerabilities, tsunami, doomsday, It's of course not a new problem per se. Bugs have really plagued us for as long as there's been computers. There was a bug that caused the Ariane rocket to blow up. We've had long before AI was to blame for things, massive outages causing billions of dollars. But there's clearly an uptick, and we're getting more and more brazen things. And once a lot of people get their accounts hacked, some of those people who get their own accounts hacked will be administrators for GitHub repos of popular packages. And then things like this can happen where a malicious update to some package that you use is pushed by someone you thought you could trust, but it wasn't them, of course. It was the hacker. You pip install something. Now all your credentials have been uploaded to the internet. What do we do about this? Remember Homer Simpson, right? So clearly the reason we're getting more of this has a lot to do with the increased availability of great hacking tools from AI, but AI can also help. Now, one way it can help, of course, is what Anthropic's Project Glasswing is trying to do. Let you use something like Mythos to find the vulnerabilities and patch them before hackers do. Great to do that. But in my opinion, it's not enough, because we'll always be stuck in a cat and mouse game that way. There's also something else. It's even better that we should be doing in parallel, which is to make sure there are no bugs in the first place by changing the way we make the code. So let's look a bit more at this, and I'll explain to you what I mean by vericoding. AI has, of course, revolutionized our ability to generate art and text and code. In mathematics, it's also revolutionizing our ability to make proofs. A number of famous Erdos problems have recently been proved with AI, for example. And if you can prove stuff about math with AI, obviously AI can revolutionize your ability to prove stuff about code as well. Prove that it meets your specifications. Prove that it has no bugs. So here's how I see the history of coding in one slide. When you write code, there are two things you would like. Minimize the effort you spend. That's the x-axis, so it's nice to be on the left. And minimize the amount of bugs. That's the y-axis. So you want to be down as close as you can to the lower left corner. We started off with traditional coding. We humans, we write the code, and there are some bugs. Now, vibe coding is all the rage, where we have less effort, because the AI writes the code, but there are still bugs. In some cases, more. The opposite extreme is to do formal verification. This was first pioneered by Alan Turing in the 1950s, And the idea is you write down a formal specification that your code should meet, the properties it's supposed to have, and you mathematically write a proof that the code meets that. The reason this is better than this debugging is because when you're doing test cases, looking for bugs with Mythos or whatever, you can never test every possible input to the program, right? So debugging and test cases will only ever be able to prove the presence of a bug, not the absence of bugs. Whereas here, what Alan Turing realizes, if you write a mathematical proof that none of the almost infinitely many inputs will violate what you want, then you can really rest easy. It doesn't matter how smart your AI for hacking gets. It can never do the impossible. The problem with this is that the cost for getting rid of all the bugs is a massive effort. It's way, 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 way more work proving that there are no bugs than it was writing the code. And that's the reason why this has not really caught on in a massive way. It has caught on in very high stakes areas. For example, chip makers tend to try to formally verify as much as they can of the hardware, because if there's a bug in the hardware, like for those of you who are old enough to remember the Intel division bug, the company can't just patch that with a software upgrade. They actually have to recall billions of dollars worth of chips and send new ones. So it's been used in these niche areas where it was worth the effort. But how can we make it catch on? How can we make it vastly cheaper and more accessible? Enter formal auto-verification. The idea here is that you no longer have to write the proof. You ask the AI to write the proof. And we did a paper, me and a bunch of MIT students, a couple of years ago, where we found that this actually AI was already good enough then that it worked 68% of the time. Tried it again recently. Now it worked 96% of the time on the same benchmark through no effort of our own. It was just the rising tide of better LLMs. But the ultimate prize is going to the lower left corner here. Almost no effort and still no bugs. That's Vericoding, where the idea is that you don't even write the code. You just write this formal specification. And the AI goes, writes the code, writes the proof that the code meets the spec, and you rest easy. It's much harder. We've been getting success rates between 27% and 82%, depending on the language, but it's improving fast. Just came back from a conference in Paris last week where many of the world's leading formal verification experts were present, and Leo De Mora from Lean, who made Lean, was there, and so on. And there was just so much energy in the room. And I'm quite confident that if we talk about this in a year's time, those percentages are going to be very high. So let's unpack this a little bit. Traditional coding, again, means we humans write the code, cross our fingers, hopefully no bugs, yeah? Formal verification means we do much more work. We also write the specification for what it means that there are no bugs, and we write the long, complicated proof, and then we have a little proof checker that says, yep, you succeeded. But so much work. If we bring AI into the picture, the AI can then, in auto verification, write the proof for us, or in Vericoding, also write the code for us. So we humans have to do very little here. If you worry that this is never going to work, because how on earth are you going to trust this, Suppose that the AI gives you a code that's 100,000 lines long and a proof that's 10 million lines long. How are we possibly going to trust this, especially since we don't really understand how these large language models work? We don't really trust the AI. Here's the really, really good piece of news, which is maybe my single most important message today. You don't need to trust any of those things. Just like it's harder to find a needle in a haystack than it is to verify that it's a needle after you found it, it's much harder to find a correct code and a proof that it's correct than to verify that it's correct, to verify that the proof is correct after you found it. Think about it. Suppose some random person comes up to you and says they proved the Riemann hypothesis or some other super famous math theorem, right? And they spent 10 years doing it. you don't actually have to trust this person. You can just take the proof and go talk to some math professor at some nearby university here whom you do trust and have them check it. And if the proof checks out, now you can trust the theorem. In the same way, you can give this super complicated machine-written code and proof to your little proof checker code on your laptop, which can be just 300 lines of Python. Very easy to understand what it's doing. Yeah, substitute this line into this, check, go through. And if it says this is all good, that's the full trust that you need. If this sounds a little bit unfamiliar, it's not if you think about it in the right way. In the early days of programming, people used to write machine code. They used to write punch cards. I remember back in the 80s, I wrote this computer game, and it was so slow I had to rewrite everything in assembler. And nowadays, we don't do that. We write in a much higher level language. And then we have a compiler that converts this higher level, more human-friendly description, shorter description, into the machine code. This is taking the idea of compilation to another level, where you actually just write the specification of what the program is supposed to do. So, for example, raise your hand if you ever compressed a file with a gzip or something like that. Right? You can easily write down a specification saying, I would like to be able to prove that if I compress any data and then uncompress it, I'll get the same thing back. I want to be able to prove that. And then if you have many different compressors, you can just compare which ones compresses best and fastest, and you go with that. It's easy to specify this, really hard to write the code, and very hard to write the proof. So this is how I think we're going to be programming more and more in the future, where we just have to explain what we want. An even higher level than a high-level computer programming language, and then with AI's help, we do the rest. If you want to dive deeper in this is a paper we wrote on Vericoding, where we built the world's largest benchmark to test it on, about 12,000 programs. And as I mentioned, it's beginning to work. The percentages here aren't great, but they're right. Every time there's a new LLM release, they get better. And I'm quite confident that these percentages will start saturating pretty soon. And what's going to happen here, I think, is we're going to get a virtuous cycle. The AI's capability to prove stuff about code is very limited by there being so little of it, so there's not much to train on. Once you get a bit of more adoption, will have much more formally verified code. The AI companies can train on this, and then we're going to get much better AI tools. We get more adoption, and around we go. Now, quiz. What does the O stand for in the name of this conference? Open, yes. So my question I have is not whether this is going to happen. I'm quite confident that we're heading towards a future with provably bug-free code written and proven by AI. The big question is it going to be mostly open tools that everybody can use for free that will lead to very rapid adoption, or is it going to be mostly closed stuff that some companies will do in a closed way and try to patent it and keep people from doing it open, and thereby really slowing down adoption and stifling innovation? I'm fighting very hard for it to be open, so that's why it's extra fun to talk with you here today. And to help with this, I've been working a lot with many colleagues around the world to build open tools for this and just release them to the world so the community can start working on this quickly so it becomes more like Linux and less like some arcane proprietary thing that stifles innovation. For example, we built this collaboration tool called Verilib, where a lot of people can collaborate, sort of like Google Docs style on big projects. Raise your hand if you have Signal Messenger on your phone, the app. For example, to jumpstart this, we're doing a big project of formally verifying Signal Messenger, so you can get an actual rigorous proof that no one can read your texts, except those who you want to read it. And we've already successfully finished formally verifying as of last week the crypto package that it uses with elliptic curve cryptography. And you can see the status of things, and blue means that people have written the formal specifications, green means the proof is there, it's already. If raise your hand if you've ever worked with Rust. A few Rusties. So in general, whatever language you work in, here is some Rust code with a specification. In this case, what we're doing is it gets automatically translated into a different language, Lean, which is tailored for proving things about stuff. And no need to get into the weeds here, but this is an open community. Everybody is excited about this, is welcome to join and use all our tools for free. Another thing I think is crucial to have open is the standard for trust. So things being bug-free and so on are maximally valuable if people can trust which things are actually bug-free and which ones just claim to be bug-free. So if you go, for example, to the website of this elliptic curve cryptography package I mentioned, it has a little badge on it, a little green check mark saying it's certified. What does that mean? Well, if people click on it, they come to this trust certificate that we issued with our collaboration. And the idea here is to make it really easy to trust things that should be trusted, and it's very easy to not trust things that should not be trusted by combining, first, transparency. It has to be really obvious, just stated very clearly, what exactly is it that has been proven with what assumptions. That's the transparency. It has to be reproducible. Nobody should need to trust me or whoever issued this trust certificate, because it should be trivial for any user to just reproduce the whole thing. So we've made it such that if you just type a command on the Unix command line here, it downloads a Docker container with all the tooling, it runs it, might take half an hour or so, and then checks, yeah, this actually checks out. Third, it has to be very usable. It has to be possible for people who are not hardcore nerds and want to do a PhD in formal verification to also trust. Traditionally, we do this with authority. If you walk into a grocery store and pick up some milk and it says organic on it, there's a little certificate there saying USDA organic. So you have to trust that some part of the US government has actually certified, that this is actually farmed in the way it's supposed to be farmed, etc. Here, we would like to avoid having to trust anybody at all. So we're using a crowdsourced model for trust instead, where because we make it so easy for anyone to test, reproduce the whole process by just downloading stuff, running it, right? It's sort of like if it were very easy for someone to chemically analyze the milk and check if it has pesticides in it. In this case, it is very easy. So if someone comes along, someone's grandma, who just wants to text securely or whatever, she will know that probably a whole bunch of nerds have already rechecked this themselves, and if anyone had found that the issuer of the certificate had lied, or that we had lied when we put this up, we would have been caught and humiliated publicly all over the internet, and and it only has to happen one single time, right? That we put out one fake trust certificate and our reputation is shot forever. So this is a way you can crowdsource trust. Now, I want to add a little bit more optimism. This, I think, will not only be helpful for getting rid of those pesky bugs, those vulnerabilities that enable so much hacking and cause so much damage, but it will also be relevant more broadly as AI gets more and more deployed, AI systems get deployed more and more in our society. If one of you, for example, with your neural network that you have in your brain, in your head, which learns a new algorithm, you figure out a new algorithm to fly a rocket to to the International Space Station, say. And I really want to trust that this rocket is going to get there safely. How do I do this? I have two choices. Either I could take you and strap you into the rocket to tell you to steer it, and then to build trust, I could try to do a bunch of neuroscience research on your brain, try to figure out how does your brain really work. Neuroscientists have been trying to figure this out for a very long time. They're still nowhere near done. And it's kind of analogous to how people today try to figure out exactly how ChatGPT works under the hood. I've worked on this a lot with my MIT group, and trust me, we're nowhere near understanding well how they actually work. But there's a much easier approach. I could just be like, hey, Arun, could you be so kind, just this algorithm you came up, could you just code it up for me in Python or Rust or something? And you'd be like, fine, yeah. And then we could formally verify this. Not only do we now get complete trust that the rocket's going to fly the way we want, but you don't have to stay awake 24 hours a day and banned from bathroom breaks. It's just a total win, right? Now, so in other words, the way I think about this is you, Arun, you can actually export a significant fraction of the algorithms and data that you have learned with your neural network. And once it's been exported, we don't have to understand how the brain works and how you learned it. A cat, on the other hand, no matter how cute it is, has an exportable fraction of about 0. If it figures out a new algorithm for catching mice, it cannot code that up in Python. It can't even explain it in English to other people. So I have a conjecture, a very optimistic conjecture, that the exportable fraction, the fraction of the learned algorithms and data and knowledge that's in a neural network that can be exported grows monotonically as the intelligence increases. 0 for a cat, pretty high for humans, and as we get closer and closer to AGI and superintelligence, my conjecture is it's going to converge to 100%. Now, suppose that's true. What does that mean? It means something awesome. It means we actually don't have to deploy these untrusted black box neural networks in safety critical situations any more than we have to deploy you to fly the rocket to the space station, Arun, right? Instead, what we would do is we humans, we would write down the specification of what we want. We go to this future extremely powerful AI and say, I want this app, or I want this tool for my company. Go build it. It goes away, comes back 24 hours later. Here's the whole code base. Here's the proof that it meets your spec. I feed it through my proof checker. And now I deploy that instead. I never deploy the black box neural network any more than I strap you into the rocket. Finally, let's talk. I want to say a little bit about how I think. So this is the caveat to that, right? Is that today we humans cannot export yet 100%, and AI systems can certainly not export 100% of their algorithms into code. There's some percentage that keeps rising. But I'm an impatient person. If we can do something great for the world, I want to see it also. How much can we do right now, even if it's going to get better later? So let's talk a little bit about this. You all have, if you guys were made of silicon, we would say that you are all AGI, because you have human-level intelligence. Specifically, I find it helpful to separate the intelligence superpower that you have into 3 parts, 3 superpowers. One is domain intelligence. You might be really good at playing chess, really good at driving. That's the bottom one, the I. Second one is generality. You can do so many different things. Third one is autonomy. We had a wonderful talk right before this about agents. And you are all agents. You can go out and do things in the world. Now, the interesting thing is, you have all 3 of these superpowers combined. But even if you build AI systems that only have 1 or 2 of them, they can be very useful. And they are, so if you can only export a small fraction, non-complete fraction of all the knowledge, you can still build a lot of very cool tools today that are written by AI in traditional code. You can have things that are highly autonomous, robotic lawnmowers, et cetera, which are very easy to prove things about, and you might want to prove that it's not going to go into the neighbor's garden or mow your cat or something. You can have self-driving cars, as an example of something which are both very autonomous and very domain intelligent at driving, but you don't need them to have all sorts of other floofy knowledge like how to make bioweapons or how to persuade you to vote for your least favorite politician. You might want your car to just stick to driving really well. And almost all the angst I hear that comes from the rapid rise of AI comes precisely just from insisting on building these giant black box AI systems that have all three superpowers in one, combined: autonomy, generality, domain intelligence, all at top level. That's not what the market usually needs. What we really want are products that do specific tasks. Very rarely do they have to do all of those things at once. Moreover, it's much easier to control them and have them improve stuff about them if they're a little bit narrower. And extra bonus, if AI doesn't have all three superpowers, it can never take your job because you have all three superpowers. So let's just end by looking at a few examples of really cool things you can do without building full-blown AGI or superintelligence that has all the superpowers, but that is narrower. This narrower AI is what I like to call tool AI. We can save over 1 million lives per year from ending pointlessly on the world's roads, with tool AI, without AGI. We can save even more lives, according to a study, by preventing stupid mistakes in hospitals with tool AI. We can diagnose prostate cancer, lung cancer, and countless other diseases incredibly well now with narrow tool AI without AGI. Really revolutionizing and democratizing diagnosis in medicine. We can improve pandemic discovery and prevention. We can figure out how to fold proteins. We can revolutionize drug discovery and drug development. You can even win a Nobel Prize for this with tool AI without AGI. AlphaFold had only one of the three superpowers, domain intelligence. It's not even agentic at all, and it's really not general at all. It doesn't even speak English. We can improve all sorts of industrial processes and research in labs with amazing robotics. That's tool AI, quite narrow. This robot has no ability to persuade you to vote for your least favorite politician or persuade your child to have it be its AI girlfriend, because it can't even talk. And it doesn't need to for this task. It's a tool AI. You can use tool AI to reduce electricity consumption, make the world more sustainable. Very close to my heart is using tool AI for making education more accessible, more personalized. And McKinsey has this nice report showing how tool AI can really revolutionize pretty much every sector of our economy, producing massive gains. There's just so much exciting stuff one can do. And finally, looking globally, the United Nations Sustainable Development Goals, which have been endorsed by pretty much every country on Earth, US, China, Europe, etc. We wrote this paper showing that with good AI tools, we can accomplish these goals much, much faster. So I want to end there. I think there's too much pessimism right now, where people just are obsessing about this idea that we have to rush to deploy these giant black boxes and hope somehow that they don't have bugs in them and aren't going to behave in ways we don't want to. I've offered a more optimistic vision where we use AI itself, untrusted AI, in fact, to have these systems export the algorithms and the knowledge that we want them to export into provably bug-free code that we can then deploy in the world and make the world a much better place. Thank you.
So we have time for a couple of questions, and thank you so much for that very insightful talk, Max.
Thanks for the talk. Formal verification always has been like an awesome promise and made a lot of progress in things like compilers. For tool AI or regular coding, the loop is sometimes like I build something. If I'm lucky enough to have someone who can do formal verification, they then check it. If they find something, I have to go rebuild it. It's done in a language that's a professional academic language of pure math, which is kind of hard to access. But it also has the benefit of being extremely rigorous. So the question is, at what point does it become accessible or sort of leverage something like an LLM to help us do the proofs while we're doing the work?
I would say that point is now, or maybe a month ago or so. We were talking about compressing files, for example. A guy who works at the LeanFro, the folks who have made this lean programming language, recently was able, just a few weeks ago, was able to do a formal proof that gzip does exactly what you want. You can compress anything, uncompress it, you get the thing back. And I think we're in the beginning now of an exponential ramp up of more and more things getting formally verified. And when things are formally verified and they're open source, right, they will immediately outcompete other alternative code that does the same thing. I mean, whether you're building a commercial product or an open source product yourself, if you're shopping around and being like, well, should I use the formally verified crypto package or the one I just have to trust blindly crypto package? Should I use the formally verified version of OpenSSL or the one where I just have to cross my fingers? It's pretty obvious people are going to go with the verified one when it's also free. So I think this is the perfect time to start looking at your needs. Of all the code bases that you oversee, which are the ones you would be most upset if there was a bug in them? Feel free to reach out to me also, just Tegmark at mit.edu if you have some specific thing that you would like to verify, and we can get this enthusiastic community and people on your team also to just...
We have time for one more question.
I like your chart comparing Vericode with traditional verification. Basically, Vericode reduce amount of effort, but achieve the same level of the quality of traditional verification, measured by the number of bugs. So that actually let me think about Yuval Harari, the book of Sapiens. He said that the machine does not to be perfect, but it can be just better than the human, just like AI doctor versus human doctor, right? So if we change the quality on the y-axis, do you have evidence that the Vericode is better than the traditional verification?
By definition, it will be at least as good because you can put in your specifications everything you mean by good. So if it is not better, it's going to be rejected. I think generally Vericoded software will actually also be faster to run, a bit more performant, because many of you know there's a trade-off in software development usually between optimizing more and introducing more bugs. Often there's a very clean, simple way to write the code where you can understand it, but then you might be able to put in all sorts of special optimizations to run better on this hardware and so on, which will make it maybe go 20% faster. But then you have that lingering fear in your stomach that you just added a bug somewhere, and now you can rest easy knowing that there is no bug, so you can optimize without fear.